Question 4 of Unit 3, June 2019 paper. So this is a question about standing waves, and the student is carrying out an experiment to determine the mass per unit length nu of a string, and we can see the standing wave that is produced. So this will be like the third harmonic. So the student recorded the following data: the length of the string, the frequency, and the mass. So we need to calculate the mass per unit length, the mu, using the equation below. Right, so first of all, we need to rearrange this equation in terms of mu. Right, so I'm just writing this equation again. So mg over nu equals frequency times wavelength. So I have to get rid of the square root. Therefore, I will put both sides into the power of 2. This one cancels out the square root. Therefore, I'm going to have mg over nu equals frequency square wavelength square. Then I'm just going to rearrange these in terms of mu. So mg equals frequency square wavelength square equals mu, and then I need to substitute the values that I have. So mass is given as 0.25 times g. We know g is 9.81, is on the datasheet of the paper, and we subtract that with the frequency, which is 105, and we square that, times the wavelength. Now, the wavelength, we're going to find the wavelength from the diagram. So it gives us the whole length of the string, but then you can see that the wavelength is only that part, therefore is kind of 2/3 of the string, is only that part. So therefore for lambda we'll say that it's 2/3 of the length of the string, which is 1.25. That will be square. So you can pause and do the calculation on your calculator, and you will get an answer of 3.2 times 10 in the power of -4. And this is mass per unit length, so therefore it will be mass kilograms per unit length meters. Now for the next question, I have already written down the answers just to save some time and make this video a bit shorter. We need to identify two significant sources of uncertainty in the measurements of the student. So now there's three categories that can cause uncertainty. First one is about the frequency. You know, if you have done this in class, you know that we are changing the frequency until we see this standing wave. Now it's kind of hard to get exactly the value of frequency that will give us a standing wave, because sometimes it's hard to identify when the nodes are formed. The nodes in a standing wave will be the points where there's no vibration, so that will be kind of tricky to see exactly when, at which frequency we get nodes. And also similarly to that, it's hard to see exactly when the wave is having like the maximum amplitude. So first will be about the frequency. So hard to identify when the nodes are formed and when do we get the maximum amplitude. Now the next source of uncertainty, it has to do with the length. Now the length, it's a measurement that we make using a ruler, and every time we're measuring ruler there's some parallax error. And then the other one is we want to measure the length from here, from the vibration generator, until that point over there. Now that point is a bit tricky because we need to measure up to the top of the pulley, which is kind of hard to identify exactly where do we set this point to be. All right, so there's some uncertainty on measuring the length to the top of the pulley. And the third source of uncertainty comes on the mass. We are using these masses here, and this is acting like the force that keeps the string tense. And that mass, of course, we're measuring it on a balance, and it's an electronic balance. Now we're using digital balance. The only thing is we need to kind of zero them before, so we avoid any zero error on the balance. The second part of this question is to find ways to obtain accurate measurements, right? So we have to explain what we can do to avoid the uncertainties we have mentioned above. So again, starting from the frequency uncertainties, which is hard to identify the nodes and the maximum amplitude. So what do we do to kind of make this more accurate? It's just we repeat and we calculate the mean frequency. So we repeat the same thing, trying to find the frequency that gives us a standing wave. We do this, let's say, 3 times, and then we find the mean. Now, when it comes to length, we said that parallax error is one of the problems. Therefore, how do we solve the parallax error? We just make sure that we take the reading from an eye level. Now, another way to do that is using a set square to make sure that we are measuring exactly where it is. So if this is the ruler, let's say, and then you have the string on top, because the string is going to be on the vibrator here, on the pulley there. All right, so we can use, let's say, a set square if we want to measure that point over here. Then we use a set square so we can identify that value exactly, all right, or similarly to that, to find that value there. And last one for the length is, because it's a standing wave, it keeps moving, the springs keep moving, it's better if we just switch off the vibration generator, and therefore we get the string to be straight. That will be easier to measure. And when it comes to mass, if we have any zero error on the balance, then we just make sure we hit the zero button, we zero the balance before we take the measurement. Zero error, remember, is a systematic error. It's something that it's going to show in every measurement, and it's always going to be the same. So by zeroing the balance before each measurement, we kind of remove that error.